Hello people, I'm Bharat Acharya. Welcome to our new video. Today's video is probably the most important video of 8051. We are learning this topic called timer section. When you see question papers, you will understand the importance of this topic. It is important by itself. It comes as a theory question. It comes in programs as programming question. Plus, if you want to learn the next big topic of 8051 serial port, that completely depends upon your understanding of timers. So plays a big role in the exam. Okay, let's start. Now 8051 has two timers. They are two 16-bit up counters by the name timer 0 and timer 1. So first of all, let's understand what these words mean. Before that, let's first understand what is a timer. A timer is used to produce a delay. Isn't that obvious? If we say I have kept a timer for 10 seconds, maybe after 10 seconds I want to ring an alarm or whatever I want to do, that means I want a delay from now to 10 seconds. So timers are used to produce delays. There is another method to produce a delay by writing a dummy instruction like NOP and putting it into a loop. NOP stands for no operation, so it does nothing, but time is still wasted in fetching and decoding the instruction to understand that it does nothing. So if you put NOP in a loop and do the loop thousands and thousands and thousands of times, even that will give you a delay. But that kind of delay is called software delay. And if you engage a timer to produce a delay, that's called a hardware delay. A software delay is cheaper, but it involves the processor. If I write a loop, who is going to execute that loop? The processor. So the processor itself is used to produce the delay. That means during the delay, the processor can do nothing else because it's itself involved in making the delay. On the other hand, if you use a timer is a separate hardware. This is the processor, this is the timer. Processor tells the timer, count, go, count 100. It starts counting. When it finishes the count of 100, it informs the processor. So you got your delay, but who was doing the counting? The timer. Who is free? The processor. That's the whole idea. During the delay, not only are you getting a delay, but you're also keeping the processor free to do other operations. Tell me, did you understand the concept? Take a simple example of a microwave oven. Now, in an oven, you put food inside, you shut the door, you select 30 seconds and you press start. What happens? There is a delay of 30 seconds for which cooking takes place. A timer starts, waits for 30 seconds and then stops the whole cooking process. So who is going to make this delay? If you use a software delay, you have engaged the processor for this operation. If processor produces the delay, who is going to rotate the dish? Who is going to control the temperature? Who is going to display the counts on the screen, the time, the seconds on the screen? So for all that, you need your processor to be free. So here you need a separate component to produce the delay. That's where timers come into picture. Please tell me, did you understand why you're learning this chip? Wherever you need a delay, or your mobile phone, you've kept an alarm for tomorrow morning. That means that alarm will trigger tomorrow morning, let's say 7 o'clock or whatever time you get up. So you've kept a delay from now till that time. If you use a software delay, what happens? Your processor is involved in making that delay. From now to tomorrow morning 7 o'clock, you cannot use your phone. Instead, if there is a hardware delay, the processor tells the timer, you count, I am free to do other operations. When your counting is over, inform me. Did you understand this? So that's the idea. So these delays are hardware delays. Okay? Now look here. So there are two timers, timer 0 and timer 1. What is the advantage of having two timers? You can produce two delays simultaneously. I tell one timer count 1000. It is counting I as in the processor. I am free to do other operations. While I am doing another operation, I realize I need one more delay. Now if I have only one timer, that means I have to wait for one delay to get over to start the next delay. But if I have two timers, I can simultaneously engage another timer, you produce another delay. Both timers are producing delays, the processor is free to do another operation. Whichever timer, whenever it finishes the delay, will tell the processor and it will do the appropriate action. Tell me, did you understand? So what is better? Having one timer or two timers? Of course, two timers. More the timers, more the delays can be produced simultaneously. Okay, we could have had 30-40 timers also, but then there is a limit to which you can add hardware to a chip. And then there are better ways to manage them, which you will learn when you learn embedded system. How with the help of only two timers you can manage to do all your delays in a system, but that is a separate thing altogether, that's not here. So here we have two timers. So two timers are called timer 0 and timer 1. The next thing, they are 16-bit timers. Now what does that mean? What did I tell you? A timer is used to count. I am the processor, you are the timer. As an example, I tell you count. So the first thing I have to do is load a count inside you. That count is a 16-bit number. That's the meaning of saying they are 16-bit timers. So 16-bit count means I can give a count all the way up to FFFF. That means it can do 65,535 counts, which is a huge number. Tell me, did you understand this? Of course, every time you don't give it a count of 65,000, you give it a count in small numbers also, 5, 10, 15, 20, but it can be up to 65,000. Tell me, is that clear? No. So there are two 16-bit, last point, up counters. What does an up counter mean? There are two types of timers in the world, an up counter and a down counter. An up counter will count up 1, 2, 3, 4, 5. A down counter will count down 5, 4, 3, 2, 1. Both are equally good. It's like a choice of lefty and righty. There is no one better over here. It's just a personal choice or personal preference. So similarly, up counter and down counters both count. Some chips use up counters, some chips use down counters. So these counters happen to be up counters. Okay. Now, so these are your two timers. They are identical. You can study any one timer. The other does the same thing. So let's look at timer 0. The first thing, as I said, is we have to load a count. The count will be a 16-bit number. To hold the count, we will need a register to hold the count. That register will be an ordinary register or an SFR. Of course, SFR. I'm sure you know what an SFR is. SFR stands for Special Function Register. So you need some special register to hold this count. Look here. So again, if you know SFRs, there are 21 SFRs and they are all 8-bit registers. Our count is a 16-bit number. So that means you will need 2 SFRs. So each timer has 2 SFRs to hold the count. The lower byte and the higher byte. Timer 0 lower byte, timer 0 higher byte. Similarly, timer 1 lower byte and higher byte. So as you can see, there are 4 SFRs used over here, plus 2 more SFRs, TCON and TMOD, which we will come to very soon. So altogether, there are 6 SFRs used in this topic. See how big the topic is. Out of 21 SFRs of 8051, 6 are used in this topic alone. That's how big this topic is. Anyway, let's go ahead. So the first thing that we have to do is load a count. So suppose I want to load a count of 0005. Okay, 0005 is a 16-bit number, will be loaded in these 2 registers. 05 in lower byte, 00 in higher byte by instructions like this. Move 𝗕𝗃_#05, move 𝗕𝗃_#00. I'm sure you know what hash does. I'm sure everybody's seen everything modes by now. So you're loading the count 05 and 00. So moral of the story, you have given your count. Now, I've told this timer to do how many counts? 5. It will start. As you know, it is an up counter. That means it will become 6, 7, 8, etc. Once again, let's start again. We have given a count of 5. After 5, it will become how much? 6. Whenever it feels like? No. Depending upon its morning time, evening time, maybe morning time it counts faster. No, nothing of that sort. So something has to happen for it to count. For that, we need a clock. On every clock pulse, the count will change. The clock is used to trigger counting. Did you understand this? So, I have given a count of 5. On the first clock pulse, count will become 6, then 7, 8, 9, all the way up to FFFF. When you increment any 16-bit register beyond FFFF, it rolls back to 0000. That event is called a timer overflow. That's it. This is what the timer does. I have given a count, I apply clock pulses. On every clock pulse, it will increment. When it reaches 0000, that is called timer overflow. That means your delay is over. The timer has done its job. Who was free during this whole delay? The processor. The processor was executing some program. This is a program. While the processor was doing this program, timer was doing the counting. Now the counting is over. So who should be informed about it? The processor. Now there are 2 ways to do it. One option, processor keeps checking the timer. Where have you reached? Where have you reached? Where have you reached? Do you understand this is wasting the time of the processor? If the processor had to check the timer, processor might as well would have done the counting also. Either ways you are wasting processor's time. So the processor will not check the timer. It's the other way around. When the timer finishes counting, timer will send an interrupt to the processor. Please tell me, did you understand this? So the moment timer finishes counting, it will send an interrupt telling the processor that the counting is over. Are you clear? Now I'm going to say something which I want you to remember forever, at least as long as you're learning 𝗕𝗵𝗿. In 𝗕𝗵𝗿, whenever any event occurs which is supposed to cause an interrupt, first of all, some flag becomes 1. Did you hear what I said? First of all, some flag becomes 1. So over here also, there are flags called TF1 and TF0. They are called timer overflow flags. I repeat, timer overflow flags. Whichever timer will overflow, first of all, the overflow flag will become 1. Before the interrupt finally hits the processor, the overflow flag will become 1. So over here, TF0, because we are learning timer 0, TF0 flag will become 1. That is why processor will get an interrupt. It will suspend the current program, go to the ISR, where it will do whatever it wanted to do after the delay. Maybe after the delay you want to fire a missile, maybe after the delay you want to launch a rocket, maybe you want to start some shower. Whatever you want to do after the delay, you do over here in the ISR. So my point is, when you finish the ISR and come back to whatever program you were doing, should this flag still remain 1? No, because we went to the ISR because the flag was 1. If after coming back also flag is 1, obviously we will get the interrupt again we will go to the ISR and this will become an infinite loop. So instead of that, while going to the ISR, this flag automatically becomes 0. Which flag? The timer overflow flag. So let's just do this again. When the timer overflows, it makes the overflow flag 1, telling the processor I have overflown. That sends an interrupt to the processor. Processor goes to the ISR. As it is going to the ISR, it makes this flag automatically 0. So students say, then what is the purpose of this flag? Instead, when the timer had overflown, it should have sent the interrupt and we would have gone to the ISR. That would have been so simple. Now, timer overflows, makes the flag 1, sends the interrupt. We go to the ISR, the flag automatically becomes 0. So why do you need this flag? These flags are used to store the pending status of interrupts. Listen carefully. There are 5 interrupts in 𝗕𝗵𝗿. 2 are of these 2 timers. 2 are external interrupts, INT0 and INT1. I'm sure if you remember pin diagram video, these 2 were external hardware interrupts. And there is one more interrupt called serial port interrupt. The next to next video after this will be the video on interrupts. So you'll be learning it anyway. So you'll be learning all the interrupts. So my point here is, there are 5 interrupts in 𝗕𝗵𝗿. There is always a possibility that 2 interrupts occur together. Suppose these flags were not there. 2 interrupts have occurred together. Whichever is of higher priority, that will be serviced first. The idea is, after that is serviced, this one should also be serviced because this one also occurred. Now, the first interrupt's ISR can take time. It's an ISR. God knows how much time it will take. It's a program. Maybe it's small, maybe it's large, maybe it's very large. So it will take some time. When that ISR is over, the processor should not forget that there is another interrupt yet to be serviced. So somebody should have reminded the processor that I am pending. Say again, I am what? Pending. This is a technical word. A pending interrupt is an interrupt that has occurred but not yet been serviced. So pending interrupt should not be lost. So that is why whenever any of those 5 sources that I mentioned, whenever they are supposed to send an interrupt, first of all they make a flag 1. Telling the processor, yes, I have occurred. Now, it interrupts the processor. If processor is doing nothing else, it will go to the ISR immediately. Otherwise, if there is some other interrupt occurred which is higher priority or whatever reason, processor may not go to the ISR right now. That doesn't mean processor will forget that this interrupt has occurred. This flag will keep reminding the processor, I am pending, I am pending. Whenever processor finally goes to the ISR, this information is no longer required and the flag automatically becomes 0. Please tell me, did you understand? Is the role of timer overflow flags clear? Great. Now, let's do this again. First thing, we load the count. Once we load the count, we apply clock pulses. You know what we're doing? I'll tell you what we're doing. We are doing an introduction to timers. If you understand this introduction, of which only 2-3 minutes are remaining, if you understand this introduction, I promise you the whole topic will just suddenly fall down like a pack of cards. Suddenly it will become very simple. Just be with me and do this introduction very clearly. It should become very strong in your mind. I have summarized all of that in this small discussion. Okay? So the first thing that we do is load the count. After we load the count, we apply clock pulses. On every clock pulse, the count will go on getting incremented. Eventually, the timer will overflow. All this while processor was free. Timer was doing the counting, the processor is free. When the timer overflows, the delay is achieved. The timer will now send an interrupt. To send an interrupt, first of all, it will make this flag 1, reminding the processor that I have overflown. That sends an interrupt. Processor goes to the ISR. As the processor goes to the ISR, the flag automatically gets cleared. Please tell me, did you understand this? Now, what did I say? The first thing that we have to do is load the count. No. Before that, there is a small thing that we need to do. Calculate the count. Now, why do we need to calculate the count? Because these are not down counters. These are up counters. See, if it is a down counter, you give a count of 5. It goes 4, 3, 2, 1, 0 and overflows. That means exactly after 5 pulses it overflows. So if you give a count of 5, you count 5. But in an up counter, if you give a count of 5, you don't count 5. You count 6, 7, 8, 9, blah 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 blah, all the way up to FFFF and then overflow. That means you do 65,000 counts. You wanted to count how much? 5. So if you want to count 5, you don't load a count of 5. What do you load? Come on, use your common sense. What do you load? FFFF minus 5. Did you understand this? FFFF minus 5. No, it's not FFF minus 5. It is FFFF minus 5 plus 1. FFFF minus 5 plus 1. Why like this? Because if you load FFFF minus 5, then after 5 pulses, you will reach FFFF. That means on the 6th pulse, you will overflow. That means you are counting 6 pulses. You wanted to count 5 pulses. That means you've given a wrong count. It's like you want to produce a delay of 5 minutes, but you're producing a delay of 6 minutes, which is not a small mistake. It's a huge margin of error. So, what's the idea? Load FFFF minus 5 plus 1, which means load FFFF minus 4. So what happens? After 4 pulses, you will reach FFFF. On the 5th pulse, you will overflow. That means you'll end up counting 5 pulses. Please tell me, did you understand this? I'll say this again. Suppose you want to count 5 pulses. You load FFFF minus 5 plus 1. That means FFFF minus 4. Now F is 15. 15 minus 4 is 11. 11 is B. You know A is 10, B is 11. That means you are loading FFFB. So what will happen after first pulse? It will become FFFC, D, E, F, overflow. Exactly after 5 pulses it will overflow. Please tell me, did you understand this point? So if you want to count 9 pulses, what will you load? FFFF minus 9 plus 1, that means FFFF minus 8. So it will, F is 15, 15 minus 8 is 7. That means you started with FFF 7. First pulse will become FFF 8, 9, A, B, C, D, E, F, overflow. Exactly 9 pulses are counted. Did you understand? You want to count only 1 pulse. What will you load? FFFF minus 1 plus 1. That means FFFF. Exactly after 1 pulse it will become 0. That means you get an overflow after 1 pulse, so you counted 1 pulse. I can go on the whole day. I'm sure you understood the point. So, here is a formula. Count to be loaded is equal to max count minus desired count plus 1. Please tell me, did you understand the formula? Max count minus desired count plus 1 is the formula for the count. This formula applies to both timers because both are up counters. Tell me, did you understand? So, the first thing that you do is calculate your count. Based on that, you load your count and the remaining story which I've told you. Now, one last point that you need to know as an introduction before we take a plunge into the topic is, these are called timers also, these are called counters also. Now, people think a timer and a counter is the same. No, it's not the same. It's almost the same. I would say, yes. All of this that I've taught you applies to a timer also and to a counter also. A timer also counts, a counter also counts. Both will overflow. Both will interrupt. Both cases we go to the ISR. In both cases the flag will automatically become 1 and then again automatically become 0. Both cases the count is calculated as max count minus desired count plus 1. So all of this is the same for a timer and a counter. But there is a difference. The difference is in your intention. Your intention. You, the programmer. What do you want to do with this device? decides whether you're working as a timer or a counter. If you are doing this to produce a delay, that means you are interested in time, so you're making it work as a timer. If you are doing this only for the sake of counting, that means you're working as a counter. You would say, yes, we count to produce a delay. So we understand what a timer does. Using it as a timer is the most natural thing. I have set a timer for 100. That means what? In an oven, what do you want to do? You want to produce a delay. Who cares about counting? Your purpose is to produce a delay. You're counting just to produce a delay. But your idea is to produce a delay. I tell you, stand at a railway station. Stand at a railway station for 1 hour and count the number of trains that are passing. You are standing there for how much time? 1 hour. Your assignment gets over exactly in 1 hour. Yes, you are counting trains, but you don't care how many trains have passed. Your assignment terminates at 1 hour. That means you're working as a timer because you are interested in time. It's a time-based operation. I change the question. I tell you, stand at the station for the time it takes for 100 trains to pass. You are still standing at the same place. You're still doing exactly the same thing. You're counting trains. So to an onlooker, you are doing the same thing. To an outside person, a timer and a counter looks the same. But you know what you're standing there for. You're not standing there for a stipulated amount of time. You're standing there for the time it takes for 100 trains to pass. No matter how much time it takes. Here, time is not your concern. Your counts are your concern. So here you're using it as a counter. Tell me, did you understand the difference between a timer and a counter? Now, to give you more example, a timer is used to produce a delay. What is the counter used for? To count. You would say, what do you achieve by counting? A lot. There are so many industrial applications of counters. Look here. Suppose there is some company, okay? It is manufacturing something. Now, whatever it's manufacturing is passing through a conveyor belt. This is the packaging department in which one container should fit 100 products. There is a container that can take 100 products. So what do you need to do? You need to count how many products have passed. As soon as 100 products have passed, one batch is over, move the container, take the next one, and so on and so forth. Did you understand the point? So somebody has to count over here. In olden days, somebody used to sit over here on a chair and do something like this. I hope you remember the age-old method of counting. Yeah, those days are over. Now, because of people like you, because of engineers, this person has a far better life. You don't need a human being to do this. This is a simple mechanical process which can be easily automated. So in the modern era today, this is done by a laser light. It can be UV, it can be IR, whichever one you want. Mostly it's IR, but it can be any of the two. You know, VIVA is what we see, the others we can't. So infrared light. So this is a transmitter, this is a receiver. The receiver is a photocell. A photocell means the moment you throw light on it, it gets charged. So let's say it becomes logic 1. When light is not falling, it is discharged, logic 0. Now, when light is falling, it's at logic 1. When a product starts passing, it blocks the light. As it blocks the light, this becomes logic 0. When the product finishes passing, the light is again re-established. So it becomes logic 1. So in this much time, one product has passed. The next and the next. These are products. To an outside person, these are products. To an engineer, they are pulses. Next time you see products moving, understand they are nothing else but pulses. If you give this pulse as a clock input, what happens? On every clock pulse, the count will go on incrementing. That means you are counting products. Give a count as 100, that is FFFF minus 100 plus 1, obviously. So give a count of 100, tell the timer count 100. What will happen? It will count for 100 pulses, so it will count 100 products. The moment 100 products are over, it will send an interrupt, processor will go to the ISR. In the ISR, it will trigger a motor that will move this container, put the next container, and start the process all over again. That's how the process got automated. What was the purpose over here? Are you interested in time? No, who cares about time? You are interested in how many products have passed. So you are now using it as a counter. As I said, to an onlooker, a timer and a counter is the same. To the person who's using it, that person understands what is the purpose why he or she is using this device. If your purpose is to produce a delay, you're using it as a timer. If you're just interested in counting, you're using it as a counter. I give you one example, I give you 10. You'll understand very easily. These are used so much in the world. Suppose you go to a bank. You know, in a bank there is a currency counting machine. What does it do? You put a bundle inside, it flicks all the notes and counts. Again, every passing note cuts a ray of light. There is a UV laser. As it passes, it cuts the light. As it cuts the light, it creates a pulse. Those pulses are given to the counter does counting. You enter a mall today or a movie theater or any public place, an airport or whatever, you have to pass through a machine. Yes, it's a metal detector. More importantly, it's also a people counter. As you pass, there is a ray of light over there. As you pass, you're cutting it. Of course, it's infrared. Otherwise, people will be able to see and play with that light. So to avoid that, it is infrared. So as you pass, you're cutting the light. As you cut the light, you're creating a pulse. Those pulses are given to the counter counts. So it's also a people counter. Next time you pass that machine, just move on the side, look at the top. There'll be an LCD panel. On that panel, there'll be a number. As people keep passing, the number will go on incrementing. So that means you understand it's also a counter. Anyways, I can go all day about these devices. Beauty of this subject, it's a fabulous subject to learn in engineering. Whatever you learn over here, you can see it happening all around you. So this is a subject that actually makes you a techie, a tech engineer. Anyway, let's go. So the textbook answer is, which is also correct, I just made you understand from the real world point of view, the textbook answer of the difference between a timer and a counter is the nature of this clock. If this clock, you understand the frequency, you understand the significance of this frequency, this is the frequency at which you are doing the counting. If this clock is of a fixed frequency means this is the fixed speed at which it will count for the rest of its life. This frequency is never going to change. So if I know this is the standard frequency, if I know that you always count at this speed, 1, 2, 3, 4, 5, 6, 7, 8, this is your standard speed of counting, it will never change. I tell you do a count of 100, I can predict beforehand in how much time it will get over. That means I can predict the time. That means I am working as a timer. If it's a fixed frequency, in an oven, you keep the food inside, you press 30. You know what are they? 30 what? 30 seconds. So you know the frequency of counting. Are you clear? That means you're working as a timer because it's a fixed frequency. Your operation will get over in so and so amount of time. Are you clear? On the other hand, so it's a timer. If it is a variable frequency means the frequency can change at any given point of time. So that means you're counting like this. 1, 2, 3, 4, 5, 6. 7, 8, 9, 10, 11, 12, 13. You're counting at a variable frequency. I can never say when you'll reach 100. But I know you will finish your count of 100 and stop. That means here I'm not interested in time. I'm interested in counts. That means you're working as a counter. Tell me, did you understand? You're standing at a station, trains are passing. You don't know what's the frequency at which they'll pass. Especially if it's... Anyway. So you're working as a counter. Are you clear? So anyway, so if the frequency is fixed, you're working as a timer. If the frequency is variable, you're working as a counter. Look here, come on, look here. This is 8051. In 8051, there are two timers, timer 0 and timer 1. Okay. Do timers require a clock? Yes, if you understood the whole introduction. So 8051 has an internal clock. You know it's connected to an oscillator. The frequency of the oscillator is called F oscillator. That means the oscillator frequency. It's generally 12 megahertz. So that comes inside, gets divided by 12, which means it becomes 1 megahertz. That 1 megahertz clock is available all throughout the chip. Are you listening? Now, whoever wants can use this clock. Do timers require a clock? Yes. So one option, timers use this clock, the 1 megahertz clock, the internal clock. Or, if you know the pin diagram of 8051, these timers can also take external clock. There are two pins to provide clock to the timers. The pins are called timer T0 and T1. Again, the same names, obviously, T0 for timer 0, so on. So, you can take a clock from outside, you can take a clock from inside. Now tell me, please make the last 20 minutes of my effort worth it. If you take the internal clock, you're working as a what? Timer or counter? Give me one clear answer. You're taking the internal clock, you're working as a what? Exactly. You're working as a timer. Why? Because this clock's frequency will never change. If it is 1 megahertz today, it will be 1 megahertz for the rest of the life of this 8051. So if I write a program to do 1000 counts, I know it will give me a delay of exactly 1000 microseconds. 1 megahertz means the inverse is 1 microsecond. You understand? So basically I can predict the time. Whether you run my program today, tomorrow, a year later, this program will give you a delay of 1 millisecond or whatever time, whatever count you've given based on that, whatever is the delay, I can predict right now it will take this much time. That means it's working as a timer. So here is the hint. Whenever they ask an exam question to produce a delay, please use it as a timer. You cannot produce a delay using counters because counters count at any frequency. That means you're counting 1, 2, 3, 4, 5, 6, after some time I'll make 7. How do I ever know when will you stop? If you're working as a counter, your interest is not in time. Your interest is purely to count. Then you apply an external clock that can be of any frequency. Like I told you, those trains passing or those products passing will create pulses. The nodes, people passing through a machine will create pulses. Those pulses will come from external sources on T0, T1. So if you use external clock, you're working as a counter. If you use internal clock, you're working as a timer. Now, that was all the introduction. I'm sure you're wondering if the introduction was so long, how big will the topic be? No. The topic is very simple. Once you know this whole introduction, you understand the topic very easily. Okay, look here, 1 minute recap and then we start. So there are two timers, timer 0, timer 1, both are 16-bit timers. The first thing that you need to do is load a count, but for that you need to calculate the count. What is the formula? Don't look there. What is the formula? Come on. Max count minus desired count plus 1. So if you want to count 3 pulses, you load FFFF minus 3 plus 1. That is FFFF minus 2. F is 15. 15 minus 2 is 13. 13 is D. So FFFD. So the first pulse will become FFFE, FFFF, overflow. Exactly after 3 pulses, it will overflow. I mean, did you understand? Now once you load the count, you have to apply a clock. You have an option. Either you take the internal clock or you take the external clock. If you take the internal clock, you're working as a timer. External clock, you're working as a counter. Either ways, on every clock pulse, the count will go on incrementing. Eventually, it will overflow. When it overflows, it is supposed to give an interrupt. For that, first of all, it will make some flag 1. The flags are called TF1, TF0. So if you're working with timer 0, TF0 flag will become 1. We will get an interrupt. Whenever processor goes to the ISR, the flag will automatically become 0. That was your whole introduction. Now, if you understood this introduction, as I promised you, the topic is very simple. Let's start. The first thing you're learning is TCON and TMOD. Now, hear me out. In all probability, from this whole video, this is what will be asked in the exam. If you ask my experience, I've been teaching this subject since 18 years. Okay? 36 semesters. I've taught this more than 800 times, this particular topic. Easily, would be more. So, with my experience, I'm telling you, most likely question in your exam will be draw and explain TCON and TMOD. I'm talking from Bombay University's point of view, but then that's pretty much the same for most of them. If you're learning 𝗕𝗵𝗿, a teacher who wants to quiz you on 𝗕𝗵𝗿 would definitely want to know whether you know TCON, TMOD or not, because they have massive use throughout the chip. So, the first register, TCON. TCON stands for timer control. I repeat, timer control. Now, TCON is used to control the timer. TMOD stands for timer mode, from which you decide the mode of the timer. Now, in TCON, it's an 8-bit register. The lower 4 bits have nothing to do with this whole topic. They are not related to timers. They are related to the external interrupts. To the interrupts, INT0 and INT1, they are related to those. They are not related to timers. But since they are there in the register, you need to explain them. So first, let me explain to you what is related to timers, then I'll come to that. Don't worry. Now, these two flags, TF1 and TF0, I'm sure you know them very well by now. Come on, give me a clean answer. These flags become 1 whenever the timer overflows. They are automatically cleared as you go to the ISR. Tell me, did you understand? One thing to notice, do you have one flag shared by the two timers or do you have independent flags? Independent flags. What does that mean? The two timers can overflow independently. If one has overflown, that doesn't mean the other has to overflow. Any timer can overflow anytime. They have their own flags to indicate that they have overflown. Are you clear? Now, TR1 and TR0. These are called timer run bits. I repeat, they are called timer run bits. Very important bits from programming point of view. When you make these bits 1, you are saying the timer should start. It should run. When you make these bits 0, the timer will stop. Again, making them 1 will start the timer. Making them 0 will stop the timer. Tell me, did you understand? How will you make these bits 1 and 0? By instructions. TCON is a bit addressable register. That means you can access each bit individually. So, set B, I'm sure you know about these instructions. Set B and clear. So, if I write set B, TR0 and clear, TR1, that means I'm saying make this bit 1. Set means 1. Make this bit 0. Making this 1 will start timer 0. making this 0 will stop timer 1. So you can start both timers, you can stop both timers, you can start any one and not affect the other. The two timers are completely independent. What you do with one timer has nothing to do with the other timer. Tell me, did you understand this? So both timers have their own run bits, both timers have their own overflow flags. Now one very important thing to understand is these bits, these timer run bits, they become 1 and 0 by instructions. Instructions means software. So this is called software control. I repeat, it is called software control. Don't misunderstand. People misunderstand this point. Did I say it is software delay? No, I said software control. When I started this video, the first thing I made you understand is this is a hardware delay. Processor tells the timer to count. Timer counts, processor is free to do other things. You have a dedicated hardware to do counting. So it is purely hardware delay. I didn't say it is software delay. What did I say? Software control. That means you start and stop the timer by instructions, by programming. Are you clear? Now why am I stressing so much on this point? Very soon there will be a second control called hardware control. Hardware control means you can start and stop these timers by buttons. I give you a button, press this, timer will start. Like your oven, microwave oven. You select 30 seconds, you hit start. So you press a button. That is called hardware control. Did you understand? And if you do it by programming, that is called software control. Tell me, which is more convenient? Hardware control. Obviously, software control is for people like you and me. Programmers who know how to write a program. At home, somebody wants to cook food in an oven, will not put food inside and start writing programs. That person wants a button to start and stop counting. So that is hardware control. So the more user-friendly control, which is used by the layman, is hardware control, and the one that is used by the programmer is software control. So this is software control. Software control is compulsory. What does that mean? For a timer to run, the run bit must be 1. I'm saying this in very clear words, okay? I'm not mincing words, I'm not using complicated language. If run bit is 1, timer will start. If run bit becomes 0, timer will stop unconditionally. Are you clear? This is the primary control of the timer. Are you clear? So, these two bits are used to start and stop the timer. These two bits are used to tell whether the timer has overflown. Have you understood this? Now, these bits have nothing to do with timers. They are related to external hardware interrupts. The interrupts are called INT0 and INT1. Now look here. Take any interrupt, let's say INT0. If INT0 interrupt occurs, what do you know? When an interrupt occurs, processor goes to an ISR. That you know since a long time. What did you learn today? What do you learn today? In 8051, whenever an interrupt has to occur, first of all, some flag becomes 1. Do you remember that or no? So for the two hardware interrupts also, there are flags. The flags are called I1 and I0. IE stands for interrupt external. Say again, interrupt external. Whichever interrupt has occurred, the corresponding flag will become 1. So let's say INT0 has occurred, IE0 flag will become 1. That's how the processor comes to know that there is an interrupt. It will suspend the program, go to the ISR. As it goes to the ISR, the flag will automatically become 0. Are these flags required? Yes, like I told you, if both of them have interrupted together, whoever is of higher priority, which in this case is INT0, that interrupt will be service first. But that's not fixed. Priorities can be changed. When you do interrupt topic, you will come to. But anyways, the default priority is higher. So if both of them occur together, INT0 will be service first. When will INT1 be service? When the ISR of INT0 is over. Can that take time? Can that take a long time? Yes, it can take a God knows how much time it's going to take. So you cannot expect the processor will remember somehow. How will it remember? It's not a human that has a mind. You need a flag to remind the processor, yes, this interrupt had occurred. It is still pending. Please service it. So the flags will remain 1 till the time the interrupt gets serviced. When you go to the ISR, the flag will automatically become 0. So what did you understand? Technically, TF1, TF0 and I1, I0 technically are the same flags. They both have the same concept. The only difference is these are to indicate that the timer overflow interrupts have occurred, and these are to indicate that the external interrupts have occurred. Tell me, did you understand this? So for the external interrupts, you have I1 and I0. Finally, you have IT1 and IT0. IT1 and IT0 are interrupt trigger flags. They're called interrupt type, but basically they give the trigger. I'm sure you know there's something called edge triggered and level triggered. If an interrupt is recognized on an edge, could be rising, could be falling, these are active low, so it will be falling, but anyways, when an interrupt is recognized on an edge, that is called edge triggered. When it is recognized on a level, that's called level triggered. Now, suppose it's an active high signal. Okay, active high signal means when it occurs, it should be 1. If it's not occurred, it is 0. I am the processor, these are my two interrupts. I check these two pins, both are 0. I will say no interrupt has occurred. For me, for an interrupt to occur, the pin should be 1. Tell me, do you understand that? If it is 1, I will, for an active high, I am talking about active high signals, they are easy to understand. The concept is the same, but they are easy to understand. So for me, the interrupt has occurred when this pin is 1. Are you clear? When I say for interrupt to occur, pin should be 1, there can be two complete different meanings of this sentence. See, some students are average students. They just want the answer to get over. Some students learn answers to gain knowledge. If you are that second kind, you would say this statement that I said is incomplete. I said for an interrupt to occur, pin should be 1. What do you mean by saying pin should be 1? It should go from 0 to 1 in front of me, or it should be 1 when I look at it. That is the difference between edge triggered and level triggered. If I say it is edge triggered, I want to see the edge. I want it to go from 0 to 1 when I look at it. If it is already 1, I don't care. I didn't see it going from 0 to 1, I'm not interested. It's that edge that triggers me. Whereas, if it is a level triggered interrupt, all I'm interested in is the level. As long as it is 1, even if I didn't see it going from 0 to 1, doesn't matter. If it is 1, I'm happy, then it's level triggered. Consider a revolver. Okay, a revolver. Now, a revolver has a trigger. You pull the trigger, a bullet is fired. So the literature says, if the trigger is pulled, a bullet is fired. So I pull the trigger, 1 bullet is fired. I want to fire 1 more bullet. The literature said, if trigger is pulled, bullet will be fired. My trigger is pulled. Is a bullet getting fired? No. What do I have to do? Release, pull it again. Release, pull it again. So what am I interested in? The pulled position or the pulling action? The pulling action. That means it is what triggered? Edge triggered. It's that edge that's triggering me, not the level. Are you clear? On the other hand, think of a machine gun, an automatic rifle. You pull the trigger, a bullet is fired. Don't release your finger, let it still remain pulled. Bullets will go on getting fired. It is not interested in the pulling action. It is interested in the pulled position. It is level triggered. Tell me, did you understand this? On the mobile phone keypad, you are texting somebody. You press M or you hit M. M appears on the screen. Now, if you want to type MMMMM for some reason, if you want to type MMMMM, what do? You can't keep your M pressed. You have to release press, release press, release press, release press, release press. That means it is what triggered? Edge triggered. It's not interested in the press position. It's interested in the pressing action. Tell me, did you understand this? On the other hand, if you think of a computer's keyboard, you hit M, M comes on the screen. Don't release your finger. M will keep coming on the screen. It is level triggered. Anyway, I hope you understood my point. So what is better? Edge triggered or level triggered? Both. Depending from situation to situation. Sometimes you write like edge triggered, sometimes you like level triggered. So you as a programmer have the choice to decide whether these interrupts should be edge triggered or level triggered. If you keep these bits as 1 individually for whichever one you want, that means you are saying it is edge triggered. If you keep it as 0, it is level triggered. You can keep 1 as edge triggered, 1 as level triggered. That's your choice. What are these bits for? For these interrupts. What are these bits for? For the timers. Tell me, is the role of all the 8 bits clear? 1 minute recap before we go ahead. This bit is used to tell whether timer 1 has overflown. This is used to tell whether timer 1 is running. Whether timer 0 has overflown, whether timer 0 is running. Whether external interrupt 191 has occurred, whether INT1 is edge triggered or level triggered, whether INT0 has occurred, whether it is edge triggered or level triggered. Let's take an example. Suppose I say 0, 1, 1, 0, 1, 0, 0, 1. What is this number? 6. This is 9. So the whole number is 69H. So suppose there is a question in the exam. Programmer has loaded the value 69H in TCON. explain what has happened. This is a 5-mark jackpot for you. You don't have to write tons of theory. Draw TCON, put the pattern 69 on the top and start explaining. I want 1, 2, 3, 4. 4 clear answers. What's going on with timer 1, what's going on with timer 0, what's going on with INT 1 and with INT 0. Come on, I want you to say it, okay, speak it. Big difference between thinking it and saying it. When you think it, even if you're wrong, you just try to autocorrect and you fool yourself. When you say it, you commit. You know whether what you said was right or wrong. If you were wrong, at least you know you were wrong and you will not make this mistake again in the exam. Okay, so say it. There's nothing to feel shy about. If there's somebody else around you, who cares? Now, these 2 bits are for timer 1. This bit tells you that timer 1 is running. It is counting. This bit tells you it has not yet overflown. Do you understand? It is counting, but it has not reached overflow. Is that clear? The other one, these 2 bits are for timer 0. Come on by yourself. Is it running? No. Has it overflown? Yes. So it has overflown and it has stopped. It is not running. The run bit has been made 0. Are you clear? INT 1. INT 1. It is edge triggered. It has occurred. It has occurred. And it is level triggered. Okay? It has occurred and it is level triggered. INT 0. It has not occurred. It is edge triggered. Not yet occurred, but it is edge triggered. Did you understand? This tells you INT 1 has occurred. INT 0 has not occurred. INT 1 is level triggered. INT 0 is edge triggered. Timer 0, not running, it has overflown, so it has stopped. Timer 1, it is running, not yet reached overflow. Still running, has not yet overflown. It has not reached overflow yet. Are you clear? So that's your TCON register. I hope you understood TCON register. Very important from exam point of view. And so is this, the next one, TMOD. They generally come together, okay, but no such rule, but they generally come together. TMOD stands for timer modes. This is much simpler than TCON, okay, it's very light. So in this register, we basically choose the modes of the timer. These are 4 modes. We'll be coming to this in a minute. Okay, look here. The good thing is, it's an 8-bit register. 4 bits are for timer 0, 4 bits are for timer 1. As you can see, they are identical bits. That means you don't have to learn 8 bits. Learn 4 bits. The same thing applies to timer 1. These 2 bits, M1 and M0, decide the mode. Come on, you're smart enough. I'm sure. Why are there 2 bits? Because there are 4 modes. I'm sure you realize this by yourself. So 0, 0 will make the timer work in mode 0. 0, 1 for mode 1, 1, 0 for mode 2, 1, 1 for mode 3. So suppose I have kept these 2 bits as 0, 0, these 2 bits as 0, 1. I'm saying timer 0 is in mode 0, timer 1 is in mode 1. Do they have to be in the same modes? No. Can they be? Yes. What one timer does, the other timer has nothing to do with it. Are you clear? Next, C/T bar. I'm sure you would have realized what it does. Come on, this is very obvious here. C/T bar. That means this bit can either be C or T. C for counter, T for timer. So if you keep this bit 1, it is a counter. If you keep this bit 0, it is a timer. So you are deciding whether you want to use it as a counter or as a timer. If you kept the bit 0, it is a timer. That means it will use internal clock. If you kept that bit 1, it's a counter. It will use external clock. Please tell me, did you understand? Now, can they both be timers? Yes, they both can use internal clock. I'm sorry with that. Can they both be counters? Yes, you have 2 pins. It's not like they're sharing 1 pin. Then only one can be a counter. Both have their own pins. Both can be counters. Both can be timers the way you like it. Okay. So suppose I have kept this bit as 0 and this bit as 1. Timer 0 is working as a counter, as a timer, and timer 1 is working as a counter. Okay. Now, the most important bit of TMOD, important as in important to understand. Okay, there is a concept. It's very nice bit. There is a bit called gate. In electronics, whenever you hear the word gate, understand it means enable. Okay, nobody needs to tell you this. Wherever you see the word gate, gate means enable. Now read what is written. Enables hardware control. Again, enables hardware control. Don't read further. Enables hardware control. What does that mean? I want to decide whether the timer should run or not. If I want it to run, it should run. If I don't want it to run, it should stop. How do I do that? There are two ways. One is software control. Software control means these run bits. Making them 1 will start the timer, making them 0 will stop the timer. But like I made you understand 10 minutes back, software control is good for you and me. We know how to write a program. A layman cannot write a program. A layman needs simply a button. Security guard outside the mall doesn't know anything about program. Maybe that person knows and choose to be a guard. Some people like to do interesting things in life which they find interesting, but assuming in 90% cases they have no idea what's going inside. All they want is a button. They come to their duty, the duty hours start, press the button, counting will start. Now whoever will pass, counting will take place. So they want a button. Look here. So a button means what control? A hardware control, a physical button by which we can start and stop counting, a switch. So I go to the market and buy a switch, a normal tick-tock on-off switch. Okay? I buy a wire. Now, I need to connect this wire somewhere so that the timer can start or stop. Where do I connect it? Come on, look at it. I've drawn it in blue color. There's only one thing on the board in blue color. It's drawn right next to it. This wire will be connected to INT 0, which will internally control timer 0. Press the button, timer 0 will start. Release the button, timer 0 will stop. That means by this button you can start and stop counting. That means you have achieved hardware control. Did you understand? And the same thing for INT 1, which will work as a hardware control pin for timer 1. Now what did you get by this and what did you lose? You got hardware control. You lost interrupt, because the same pin cannot do two functions at the same time. Pressing a button can either start and stop the timer or can either be used to give an interrupt. The same pin cannot have two functions at the same time. So you as a programmer chooses whether you want this feature of hardware control or not. You won't get it for free. Nothing is free. If you want it, you have to sacrifice your interrupt. The same thing pin cannot do two functions. You may use one of them as a hardware control pin, one of them as an interrupt, both of them as interrupts, so both are hardware control pin, whatever you want, but you have to make that choice. How do you make that choice? With the help of this bit gate. Now if you read this, you'll understand. Gate enables hardware control. Gate decides how you want this pin to function. If you keep gate as 1, see what is written. Counting is controlled by INT X. I repeat, counting is controlled by INT X. INT X means 0 or 1. So it can be either timer 0 or timer 1, whichever one you're talking about. So what does that mean? If you keep gate 1, counting is controlled by INT X. That means you're using it as a hardware control pin. If you keep gate 0, counting is independent of INT X. Independent of INT X, that means this connection no longer exists. So pressing the button will not affect the timer. It will simply end up giving interrupts. So you choose whether you want this to be an interrupt pin or a hardware control pin. Look here. All bits by default are 0. So even this bit by default is 0. That means by default this hardware control feature is not there. By default this pin acts as an interrupt. That's why in the pin diagram its name is interrupt. But you can change it to a hardware control pin by keeping gate as 1. And as I said, you can do it for one timer and not do it for the other, or do it for both. That is your choice. So suppose I keep this bit as 0 and this bit as 1. I have said I don't want hardware control for timer 0. This connection is not there. I want hardware control for timer 1. This connection is there. INT 1 will be used to control timer 1. Tell me, did you understand this? Now what does this number end up becoming? This is D. 8 plus, you know how to count, right? 8 plus 4, 12 plus 1, 13. 13 is D. This is 0. The whole number is D0H. If the programmer has loaded the value D0H in TMOD, explain what has happened. Is again a 5-mark question. Draw TMOD, draw the binary pattern of D0 and start. Timer 0, working in mode 0, working as a timer, and we don't have any hardware control feature. Working in mode 0, working as a timer, and we don't have any hardware control feature. Timer 1, working in mode 1, working as a counter with hardware control. Again, timer 1, working in mode 1, working as a counter, that means it will take external clock and has hardware control. has hardware control means line T1 will control timer 1 internally. Tell me, did you understand TCON and TMOD completely? You've done your own self a big favor by understanding these two registers. You will see the significance of these words when you are sitting in the exam hall. TCON and TMOD alone will be worth a lot of marks in the exam. Either they'll come as a question by themselves, or if they ask you anything about timers, whether they ask you 10-mark question on timers or 10-mark question, explain the concept of timers or modes of timers, whichever way you have to explain TCON, TMOD. Moreover, even if they ask you a program based on timer, to work on timers you need values in TCON and TMOD which you will have to form as per the question, for which again you will need this pattern. So some way or the other you will be drawing them in the exam, maybe more than once also. Okay, so anyways, that was TCON, TMOD. Now everything you learned in TCON and TMOD can be summarized in this single diagram. This is called timer counter logic diagram. It contains everything you learned over here. Okay, let's start. So this circuit is there for both timers, timer 0 and timer 1. It's the same circuit. Obviously you don't learn it twice, you learn it once, but you have a similar circuit for timer 0 as well as for timer 1. Now what does this circuit do? It is giving something to the counting stage, but it's saying clock to counting stage. That means there is a clock coming over here which will go to the counting stage. Counting stage means your count registers. This is the counting stage. The continuation of the diagram goes into the modes. So this is the counting stage. So they have a count register. What do you give to the count register? You have loaded a count, of course. What do you give it for counting? The clock. So this is the circuit that decides how the clock will come. What do you know? It can either come from internal source or external source. So there it is. This clock can come either from F oscillator by 12. F oscillator, you can see there is a two-way switch, so there are two options. F oscillator by 12, that means internal clock. That means you're working as a timer. Or it can come from T0, T1 pins. That means external clock. That means you're working as a counter. Who decides whether it's working as a timer or a counter? C/T bar. So whatever value you put in C/T bar will actually control this switch. If you kept C/T bar as 0, you're working as a timer. If you kept it as 1, you're working as a counter. So based on the value you keep, this switch will decide which clock to take ahead and give. Now that clock has come here. That clock should reach the counting stage. For that, this gate should be enabled. That means this line should be 1. Only when this line is 1, this clock will go ahead. If this line becomes 0, this switch will become open, the clock will not go there. Are you all clear? Do you want the clock to go there? Of course, otherwise how will counting take place? That means this line decides whether counting will happen or not. That means here your controls will come into picture. Software control and hardware control. What did I tell you? Software control is optional or compulsory? That is compulsory. Software control is always there. For a timer to run, the run bit has to be 1. Hardware control is optional. You can get hardware control, but you lose your interrupts. If you don't want hardware control, you will have your interrupts. Irrespective, software control is always there. Now, whatever I said will be true over here. This line should be 1. For clock to reach there, this line should be 1. For this line to be 1, look at this. The gate is an AND gate. When does an AND gate give a 1? Only when both inputs are 1. Condition simple. Both inputs should be 1. So the first line says TR1, TR0. What are TR1, TR0? The timer run bits. The run bit has to be 1. Did you understand this? Whichever timer this circuit is for. If it's for timer 0, we talk about TR0. Similarly for timer 1, it will be TR1. So if this bit is 1, only then the answer can be 1. The moment this bit becomes 0, end of story, counting cannot take place. So the primary control is your software control. Tell me, did you understand this? Further, so this bit should be 1. That is necessary. Is it sufficient? No. You understand the difference between the words necessary and sufficient. This is necessary. This bit has to be 1. But it's not sufficient. Even this bit has to be 1. Now this comes from this gate. What gate is this? OR gate. When does an OR gate give a 1? When something is 1. Either both should be 1 or at least something should be 1. Both cannot be 0. Come on. If you kept gate as 1, come on, look here. What do you do? When you keep gate as 1, you are saying you want hardware control. Am I right or not? See the effect. When you keep gate 1, after inverter, gate, you understand is an inverter. If you keep gate 1, after inverter, this line will become 0. For an OR gate to give a 1, something should be 1. If this line is 0, everything now depends upon INTX. Only if INTX is 1, this will become 1, this will become 1, and the clock will go ahead. Did you understand? If INTX becomes 0, output of this OR gate will be 0, AND gate something becomes 0, answer will be 0, this will be 0, the clock will stop. That means with the help of INTX, to which you will connect a wire with a button. So with the help of that button, a layman can start and stop counting. Press the button, counting will start, switch off the button, counting will stop. Did you understand this? That means, have you got hardware control? Yes. What did you lose? Interrupt. The same pin cannot do two functions. How do you make a choice whether you want interrupt or hardware control? Gate. You kept gate 1. That is how this pin gets to control counting. Keep gate 0 if you don't want hardware control. If interrupts are so dear to you that you don't want hardware control, that's your choice depending on the system you're making. Excuse me. So if you keep gate bit 0, after inverter, this bit will become 1. In an OR gate, if one input is 1, unconditionally the answer is 1, irrespective of the other input. Whether it is 0 or 1 is immaterial. So something which was so important in the circuit has now been just removed. INTX has no role to play over here. If this line is 1, the answer is always 1. Now the only way to start and stop counting is your software control, which I said is compulsory. Software control is always there. Whether you have hardware control or not is your choice, but software control is always there. So this is the only method then to start and stop counting, because you have kept gate as 0. If you keep gate 1, then you can control even by hardware using INTX. Tell me, did you understand the diagram? 1 minute recap, come on. From here, we decide whether it is working as a timer or whether it's working as a counter. That clock moves on. For it to reach the counting stage, this switch should be enabled. This yellow line should be 1. AND gate will give a 1 only when both are 1. So the first condition is that the run bit should be 1. Did you understand this? That's your primary control. Second condition, this line should be 1. It comes from an OR gate. OR gate gives a 1 only when something is 1. If you keep gate 1, after inverter you get a 0. Now everything depends upon INTX. Only if INTX is 1, this will be 1, this will be 1, counting will happen. If INTX is 0, this will be 0, this will be 0, counting will stop. That means you have got hardware control. Have you lost software control? No, that is always there. That bit is 1 only, then all this is true. But you lost your interrupt. If you want your interrupt, keep gate bit as 0. After inverter, this will be 1. In OR gate, if one input is 1, the answer is always 1, irrespective of the second input. That means INTX has nothing to do, no role to play over here. So for the last time, if you keep gate 1, counting is controlled by INTX. If you keep gate 1, counting is controlled by INTX. So you have hardware control. Keep gate bit as 0, counting is independent of INTX. If gate is 0, this becomes 1, counting is independent of INTX. That is the time counter logic diagram. Now tell me, did this diagram explain whatever you learned over here? Exactly. So what am I trying to say? If you're a smart student, when they ask you draw and explain TCON, TMOD, of course you're going to explain that, but to ensure that you get full marks, at least draw this diagram. If you have the time, also explain it, but at least draw this diagram, because this is not different from that. This is just a diagrammatic representation of what happens. Over there, you just saw how the bits are decided by the programmer. Here you see the effect of that on the circuit. Okay, so please go ahead. Now, we're going to learn the last part of the answer, the modes of the timer, for which I just need to move the camera over here so that you have a clear screen. Okay, so now we're going to learn the modes of the timer. This is very easy and very light. So this is mode 0, mode 1, mode 2, mode 3. Mode 0 is called 13-bit timer, 16-bit timer, excuse me, 8-bit with auto reload, and 2 8-bit timers using timer 0. Okay, let's start. I'm going to explain, to be honest, I'm going to explain only the first mode. That's what I do in the class also. Once you understand the first mode completely, you will be able to answer all the modes by yourself. Okay, you just have to understand one mode. Now, mode 0 is called 13-bit timer counter. This is TLX, this is THX. Timer 0 lower byte, timer 0 higher byte. Okay, or timer 1 lower byte, X means 0 or 1. So this is the low byte of the timer, this is the higher byte of the timer. Okay, now do you understand between these two they hold the count? Whatever is your count will be held in 0005, so it will be 05 in the lower byte and 00 in the higher byte. You understand that? Now, what have I told you? On every clock pulse, the count will increment. That means for it to count, it needs counting. It needs clock. That clock comes from this diagram. This diagram gives the clock to the counting stage. Now you're not going to draw that diagram 4 times. That is constant. That diagram is constant. Now you're seeing how the counting takes place. So instead of drawing the whole diagram, we just write clock from input stage. The clock from input stage in every case. Okay. Now, so this is the clock. So on every clock pulse, what do you know? The count will increment. Eventually, after a long time, it will overflow. When it overflows, you know it is supposed to send an interrupt, but you also know before that something has to happen. The overflow flag has to become 1. The flag is called TFX, can be timer 0 overflow flag, that is TF0 or TF1. So when the timer overflows, the overflow flag will become 1, because that will get an interrupt, we will go to the ISR. As we go to the ISR, the flag will automatically become 0. That's your explanation. Tell me, did you understand it or not? Now, there is one common mistake many people make. And they make it in all the 4 diagrams because they make it very innocently. As a student, you may not even notice that you're making this mistake. But for an examiner, it's a very big mistake, and he or she is entitled to cut all the marks of the diagrams if that mistake is made in every diagram. What is the mistake? Look here. I've written lower byte over here and higher byte over here. That's how it should be written. Students write it the other way around. Not their fault. It's a normal tendency. I have a number 35. 3 is the higher nibble, 5 is the lower nibble. So we always have a tendency of writing the higher on the left and the lower on the right, because that's how it is. But not in this diagram. Not in this diagram. Why? Suppose I have a number 35. I tell you increment this number. Increment means add 1 to this number. Tell me, what is 35 plus 1? 36. So where did you add 1? To the higher or to the lower? You sure, right? You added 1 to the lower. Keep that in mind. So 35 plus 1 will become 36, 37, 38. 39. Now suppose they are decimal numbers. This time if I want to increment the number, where will I add 1? To the higher or to the lower? You always add 1 to the lower. Come on, you don't add 1 to both, you don't add 1 to higher. Since childhood you've been doing addition. Addition plus 1 can only happen over here. You only increment the lower. When the lower overflows, it increments the higher. You did not add 1 to both. You added 1 only to the lower. Tell me, did you understand this? Now 40 will become 41, blah blah blah, blah blah blah, 99. This time when you want to add 1, you will add 1 to the here. You always add 1 to the lower. When the lower overflows, it increments the higher. When the higher overflows, the number has overflown. Did you understand this? That is exactly what this diagram is showing. On every clock pulse, the lower byte will increment. Suppose your count was 1, 2, 3, 4. This is 1, 2. This is 3, 4. Every clock pulse will only increment the lower byte. Did you understand this? 1, 2, 3, 4 will become 1, 2, 3, 5, not 1, 3, 3, 4. If you draw it the other way around, you're drawing rubbish. You may think it's almost the same. What's the difference? Just lower, higher. That is the whole idea of the diagram. You're changing the entire working of the timer. Every clock pulse will increment the lower byte. So it will become 1, 2, 3, 5, 1, 2, 3, 6, 1, 2, 3, 7, all the way up to 1, 2, FF. Still, every clock pulse will increment the lower. When the lower overflows, it increments the higher. The clock doesn't increment the higher. It's the overflow of the lower that increments the higher. Please tell me, did you understand this? So it becomes 1300, then 1301, 1302, blah blah blah, all the way up to FFFF. Still, you will increment only the lower. When the lower overflows, the higher will increment. But if the higher overflows, the overflow flag will become 1 and we will get an interrupt. Tell me, is it correct to draw it the other way around? You understand, examiners are entitled to give you a straight 0 if that mistake is made in all these 4 diagrams, because it's not a silly mistake. It simply means you don't know how this diagram works. Okay, so be careful about that point when you're drawing this diagram. So, for the last time, how do you explain this one? On every clock pulse, the lower byte is incremented. When the lower byte overflows, the higher byte is incremented. When the higher byte overflows, the overflow flag becomes 1. We get an interrupt. We go to the ISR. As you go to the ISR, the flag automatically becomes 0. Did you understand this? I just went so fast because you already know it. I'm just revising. Now, the last point, the lower byte is used as 5 bits. The higher byte is used as 8 bits. 8 plus 5 is 13. So the max number of pulses to be counted is 2 raised to 13. You can write it as 2 raised to 13. You can write it as 8k or 1FFF, however you want to write it. 2 raised to 13 is an exponential way of writing it. 2 raised to 13 is 2 raised to 3 into 2 raised to 10. 2 raised to 3 is 8. 2 raised to 10 is a k. So it becomes 8k. The other way to write it is 1FFF. Why 1FFF? 2 raised to 13 means 13 ones. Put 13 ones, you get 4 ones, 4 ones, 4 ones and 1. 1FFF. Write it the way you want. It's all the same number. But do write it. If you want full marks, please mention this. The max number of pulses to be counted is 1FFF. Please tell me, are you clear? 2 raised to 13. Now, I'm sure you're wondering why this is 5 bits. It should have been all 8 bits. There is a reason. All 8 bits also is there. That's the next mode, which is just the same mode, but instead of 5 bits is full size. Now, since this you don't have to write in the exam. This is only for knowledge point of view. Only purely for knowledge point of view. If you want to know what these 5 bits are, otherwise just move ahead by a minute. On every clock pulse, the lower byte increments. When the lower byte overflows, the higher byte increments. You understand that? If the lower byte is used only as 5 bits, that means it will overflow after 2 raised to 5 pulses. You understand, right? 5 bits means it will overflow after 1, 1, 1, 1, 1. 1, 1, 1, 1, 1 is 31. 0 to 31 are 32 numbers. That means it will go from 0 all the way to 31 back to 0. That means 2 raised to 5, 32. So after 32 pulses, it will overflow and give a pulse over here. So what do you understand? 32 input pulses will give you 1 pulse over here. Another 32 pulses will give you 1 more pulse over here. Another 32 pulses will give you 1 more pulse over here. That means this frequency is this frequency divided by 32. Tell me, did you understand this? This is also a clock, this is also a clock. Whatever frequency is coming here, it's getting divided by 32 and moving ahead. Now when you do serial communication, that's going to be our next video after we do timer programs. You'll come to know. In serial communication, the baud rate formula is 2 raised to S mod upon 32 into timer 1 overflow rate. No. Relax. I'm not even taught you that formula. All I'm trying to say is, if you pay attention, what is the formula? 2 raised to S mod upon 32 divided by 32. That means, can you see there is a division by 32? And this is a mode to divide a frequency by 32. You think it's a coincidence? No. This mode is used to create an artificial serial port where you can divide a frequency by 32 and get the same baud rate which the actual serial port does. Only because you wanted to know. You don't have to write this in the exam. You're not reproducing a whole textbook. I know it, so I'm just sharing it with you. Is that clear? This mode is used to divide a frequency by 32. It is a natural mode to divide any input frequency by 32. Okay? Most important, the mode can do 2 raised to 8 per counts or 2 raised to 13 counts, that is 8k counts. Are you clear? Now, once, as I said, you understood mode 0, you will understand all the modes now. It's just a few minutes and you're done with the video. I know it's been long. I'm talking non-stop. But you need it. This topic is not small and the relevance of this topic for the whole of 8051 is very much. Okay? So it's time spent, but spent for a good cause. Look at mode 1, 16-bit timer. Very easy, explain by yourself. It's the same. Instead of 5 and 8, it is 8 and 8. Go on, I want to hear you. Excuse me. From input state, that means clock pulses are coming. On every clock pulse, lower byte will increment. When the lower byte will overflow, higher byte will increment. When the higher byte will overflow flag will become 1. We will get an interrupt, we will go to the ISR. As we go to the ISR, the flag will automatically become 0. Same answer. The only difference is both of them are 8 bits. So the max number of pulses you can count is 2 raised to 16 or 64k, however you want to say it. You can do 64 counts, 64k counts. Do you understand? This is the biggest of all the modes. That is 13, this is 16, this is 8, this is again 8. That means this mode produces the biggest possible delay. So this is the most preferred mode to produce a delay. The point is, when you are asked in the exam to write a program to produce a delay, your first choice should be mode 1, because whatever delays these cannot produce, that can produce mode 0. Whatever mode 0 cannot produce, mode 1 can produce. What mode 1 cannot produce, cannot be produced. So, always preferably use mode 1 to produce delays, okay? Because it has the biggest timer. Its purpose, every mode is created for a purpose. This mode was created to divide a frequency by 32. This mode is created to produce a delay. When you learn these two modes, you'll also understand their purpose. Every mode has a reason why it's created. Just one second. Yeah. Now, we start with mode 2. The name of mode 2 is 8-bit timer counter with a reload. 8-bit timer counter with reload. Now, what do you understand by the word reload? Come on, you're a smart person. Reload. What is being reloaded? The count. Random count or original count? the original count. When will it be reloaded? During counting or after counting? After counting. The moment your count is over, the moment it has to overflow, at that time the original count will be reloaded. So what is the advantage? It will start all over again. It is a self-reloading mode. Without the intervention of the programmer, this mode will produce repetitive delays. So if I want to fire a missile after 1 minute, I will use mode 1. Are you mode 1? Mode 1. Are you understanding? Mode 1. If I want to fire a missile. But if I want to fire a missile after every 1 minute, without having to do the whole program again and without having to start it again, by itself go on firing again and again, then I will use mode 2. Why? Because it will self-reload and keep doing the procedure again and again. Please tell me, did you understand this? We can also reload, but I don't want to reload it myself. I want it to automatically reload. Did you understand? Now, you may wonder why is it an 8-bit mode? That is very obvious. What is going to be reloaded? The count. Random count or original count? The original count. Are we going to give the count? No. The system has to store a backup copy of the count. That means the system has to make 2 copies of the count. One will be used for counting, one will be used for reloading. To make 2 copies of the count has to be an 8-bit count, because your whole register is 2 8-bit registers giving you space of 16 bits. If your count itself was 16 bits, both your registers are occupied in holding the count. Where will you store the backup copy? Please tell me, did you understand this? So that is why it's an 8-bit mode, so that you can make 2 copies of your count, one for counting, one for reloading. So suppose your count is an 8-bit number like 35. We put 35 in both TLX and THX. On every clock pulse, TLX will increment. So this is the one used for counting. TLX will increment. Eventually it will overflow. As you can see, when it overflows, 2 things will happen. First of all, it will make overflow flag 1 and send an interrupt, because the counting, this count is over. At the same time, it will enable this buffer, which will enable a reload. Enable a reload means the value of THX will now be loaded back into TLX. So TLX started with 35, became 36, became 37, all the way up to FF. After FF, when it overflows, instead of going back to 0, the same time THX will reload back 35. That means the count will again become 35. So it starts from 35, will count all the way up to FF, back to 35. Will count all the way up to FF, back to 35. That means it is a continuous mode. All the other modes are single modes. Single modes means when they finish counting, they stop. I repeat, all other modes are single modes. When they finish counting, they stop. Did you hear me? On overflow, they stop. But this mode doesn't stop on overflow. The moment it overflows, it self-reloads and starts again and again and again. So you may wonder, then how will it stop? Don't ask me that question. You know there are ways to stop. You know there is a software control and a hardware control. Either make the run bit 0, it will stop by programming, or if you have hardware control, just press the button, it will stop. But if you don't do that, it won't stop. It will keep producing the delay again and again. So it's used at places when you want to produce repetitive delay. Like I told you, every mode has a reason for being created. This mode is created to divide a frequency by 32. This mode is created to produce a simple delay. This mode is created to produce repetitive delays. Somebody asks you, why is this an 8-bit mode? Because, why is it an 8-bit mode? Tell me again. Because you want to make 2 copies of the count. One for counting, one for reloading. TLX is used for counting, THX is used for reloading. How will it be a 16-bit mode? Where will you keep the second copy you had? So that is why it's an 8-bit mode. So you give your count to both registers. On every pulse, TLX will increment. When it overflows, 2 things will happen. First, it will make the overflow flag 1 and send an interrupt. Secondly, it will enable a reload, which will copy back the value of THX into TLX and start all over again. Tell me, did you understand this? The last and final mode. It's been non-stop talking for almost 1.5 hours. Final mode, mode 3. The name is 2 8-bit timers using timer 0. I repeat, 2 8-bit timers using timer 0. Now look here, this is a very interesting mode. From understanding point of view, we don't use it in programs ever. At least the programs that you write in from university level, you're not using it as a scientist, you're like writing at college level. So in those programs, you never really use this mode. But it's a very interesting mode to learn. Look here. So far, we had 2 timers, timer 0 and timer 1. Both of them were 16-bit timers. Both of them were totally independent of each other. Independent to such an extent that we have 2 overflow flags. timer 0 overflow flag for timer 0, timer 1 overflow flag for timer 1. So what we had is a beautiful system with two completely different timers. Are these overflow flags important? Yes, they are the relation, the connection between the timer and the processor. Timer is counting, processor in its own world. When the timer overflows, it makes the overflow flag 1, which informs the processor that the timer has overflown. So the link between the timer and the processor is the overflow flag. They both don't share one flag. They both have independent flags, which means both can independently overflow. So what you have so far is a beautiful system with two 16-bit timers. Now what we're going to do is ruin this system. Spoil this system. Why? Because of greed. Greed, you know what is greed, right? One of the 7. We have how many timers? 2. We are going to create 3 timers. How? We are going to split timer 0 into 2 independent 8-bit timers. That's the name. Read the name again. 2 8-bit timers using timer 0. So we're going to split timer 0 into 2 independent 8-bit timers. Tell me, did you understand this? I'm sure you're wondering what are we going to get. I'll tell you what we're going to get. We will get 3 timers. Timer 0 lower byte, timer 0 higher byte, and your good old 16-bit timer. These 2 are 8-bit timers, that's a 16-bit timer. But before I go ahead, tell me. Yeah, exactly. Yeah, what you're thinking is what I'm going to tell you. Good, nice. We are going to fall short of resources. It won't be such a smooth thing. Because our resources were made for 2 timers, and now in a greed we are trying to create 3 timers. Somewhere or the other we're going to fall short of something or the other. Let's see what's going to happen. First, timer 0 lower byte. Timer 0 lower byte says enough. Earlier we were 1 timer. Now let's go our own ways. Let's part ways. I want to be independent, you be independent. Timer 1, there is no problem. It is still 1. Timer 0, lower byte and higher byte want to go their own separate ways. So we start with timer 0 lower byte. Timer 0 lower byte wants to be an 8-bit timer, no problem. We give it a count, something like 35. On every clock pulse, the lower byte will increment. Eventually it will overflow. Till now what used to happen, every time the lower byte would overflow, it would go and run and tell the higher byte please increment. Now they have become separate. When lower byte overflows, it is done. Now it wants to inform the processor, look, I have overflown, even I have become an independent timer now. Now what did I tell you? To inform the processor, you need a flag. So very smartly, timer 0 lower byte uses the overflow flag of timer 0. Did you even understand what I said? The timer 0 lower byte uses overflow flag of timer 0. This flag was for the whole timer 0, but it's taken away by timer 0 lower byte. It says I called it first, it's mine. You were lazy, not my fault. Now you see this line, don't cross it. Don't come to me. This has become my flag. So timer 0 lower byte uses the overflow flag of timer 0 and has successfully become an 8-bit independent timer. Now who wakes up? Timer 0 higher byte. Says just like this one has been made an 8-bit timer, make me also an 8-bit timer. I mean, I want to work like an 8-bit timer, no problem. We'll do that also. Timer 0 higher byte, we give it a count like 40. F oscillator by 12 means clock pulses. On every clock pulse, it will also increment. Eventually, it will also overflow. Do you understand? When it overflows, see what happens. Very interesting. Timer 0 higher byte also has overflown. Now, it also wants to inform the processor, look, I have overflown. But to do that, it needs a flag. So timer 0 higher byte cannot use. It tries to tell timer 0 lower byte this flag was both our flags. It was for both of us. Timer 0 lower byte says no, I'm done. Don't come here. This is my flag. Timer 0 higher byte says it's urgent. I have overflown. I have to do something about it. How do I tell the processor? It uses the overflow flag of timer 1. Did you hear what I said? Timer 0 lower byte uses the overflow flag of timer 0. Timer 0 higher byte uses the overflow flag of timer 1 and has successfully become an independent 8-bit timer. So who lost in this bargain? Timer 1, poor thing. The problem was happening in timer 0, they used up the resources of timer 1. Timer 1 didn't even have a problem. But what has happened now? Can timer 1 count? Yes, it can count. Can it overflow? Yes, it can overflow. Can it inform the processor? No, it can't. That means it will count by itself, overflow within itself. It will never even tell the processor it has overflown because there is no flag remaining to report this. That is mode 3. Now what is your impression? This is a stupid mode. we had two 16-bit timers. Now in a greed, what have we achieved? We have got two 8-bit timers, that too the ones who work like this. And one stupid 16-bit timer that counts within itself, does not even tell us that it has overflown. So is this a good mode? Of course it is. How can it be bad? If it was not good, why would we make it? We didn't discover it underneath some tree. We made this mode. Obviously there has to be a good reason why we have done something so messed up. There is a reason. The reason is related to the next video, serial port, but you'll understand it. It's pretty simple. Now when you do serial communication, okay, listen. Serial communication means bit by bit communication. So suppose I want to send 25H. 25H is 00100101. Processor will tell the serial port, go and send 25. Serial port will send these 8 bits. Now because it's serial communication, it's going to happen one by one, which is so obvious. How can you send 8 bits on one line at one time? The same line cannot be VCC and ground both together. So they will go out one by one. What does the word one by one mean? After every bit, there is a delay. Say again. After every bit, there is a delay, a small time gap. Who produces a delay? Timer. Come on, please answer that, okay? We've been spending 1.5 hours on this. Please answer. Timers, delays are produced by timers. So what do you understand? When you do serial communication, you need a timer to produce the delay after every bit. The timer that is engaged in serial communication is timer 1. This is fixed. Serial port has internal connection with timer 1. Timer 1 is a personal timer of the serial port. That means whenever you do serial communication, timer 1 is lost because it is engaged in doing serial communication. That means you have only one timer now, timer 0. All this while you were telling the whole world, I have two timers. Whoever wants two delays, come to me, I will produce it. Now suppose somebody comes and says, we've heard you can produce two delays together. You have only one timer, you don't want to be red-faced. What do? You split your timer 0 into two independent 8-bit timers. Use up all the resources of timer 1, doesn't matter because timer 1 doesn't have to report to the processor. What did I say? Timer 1 can count, timer 1 can even overflow. It cannot inform the processor. It doesn't have to inform the processor because it's not working with the processor, it's working with the serial port. So it says, take away all my resources, I don't care. So timer 0 lower byte and timer 0 higher byte become two independent 8-bit timers. Yes, they are 8-bit, but at least they are independent timers. That means you understand how powerful this chip can get. It is mind-blowing. You can produce two delays simultaneously, plus do serial communication, plus the processor is free to do other operations. Did you understand this? Anyway, so that's why they created this mode. Now, one small thing before you just wind up, one small thing. They said God is in the details. Yeah, there are small tiny details you got to take care of. Otherwise, in spite of doing all of this, in spite of knowing such a fabulous topic correctly, you may not end up getting full marks. Yeah, they won't give you 0, but they will cut marks on these small mistakes that people make because students are very innocent. They don't know that this is a mistake till somebody tells them. Look, what have I written? TLX. What does X mean? Timer 0 or timer 1. Timer 0 or timer 1. Timer 0 or timer 1. Here, please don't write an X. This mode is only for timer 0. Timer 1 is used in serial communication. Timer 0 is split into two timers. Cannot happen the other way around. Please tell me, did you understand this? So see to it that you don't write an X over here. The name of the mode is two 8-bit timers using timer 0. This has to be timer 0. Are you clear? Another small thing. Again, very innocent mistake by a student because he or she is not aware that this is a mistake. Here, we have written clock is coming from input state. Input state means this diagram. This diagram means it can be a timer or a counter. Okay? So this mode can work as a timer or a counter, timer or a counter, timer or a counter, timer or a counter. F oscillator by 12. That means timer 0 higher byte can strictly work only as a timer, cannot work as a counter. Why? It is very obvious. It's nothing great. It's very obvious. You have two timers, timer 0 and timer 1. Both can work as timers using internal clock. Both can work as counters using external clock. This is how you are working so far. Two timers, two pins. Now what has happened? You have split timer 0 into two independent 8-bit timers. Timer 0 lower byte, timer 0 higher byte. And you have your good old timer 1. That means now you have three timers in the system. All the three can function as timers because for that they need internal clock. All can function as timers. How can all function as counters? Where will the third clock pin come from? So timer 0 lower byte can work as a timer as well as a counter. Timer 1 can work as a timer as well as a counter. Timer 0 higher byte has only one option. can only work as a timer because there is no third pin to make it a counter. You're not going to explain all this. Come on, don't be silly. If you write everything that I've been talking, do you realize I'm talking non-stop for the past 1.5 hours? To write all of this, you need more than 15 pages. You're not going to write all of this. You're not reproducing the textbook. I'm explaining to you, so I tell you so much. You're going to write it short in my book, which all my students have, and I'm sure if you're in Bombay, either ways you would have got it by now as a copy or whatever. So I have written the answer in the most precise form. Here I've explained to you all the logic. In the book, the answer in the compressed form. Get hold of the answer from wherever you can, or if you understood it, then write in your own words. Either way, don't reproduce the whole textbook. I've explained a lot because I know it and I think it's important for you to understand things properly. But cut it short when you're writing, otherwise you'll end up writing a never-ending answer. Sometimes they are sensible. They ask only timer modes. Sometimes they ask only TCON TMOD. Sometimes you get a 10-mark question, draw and explain timer section of 𝗕𝗵𝗿𝗍𝗏. That is crazy. There are about 8 diagrams in the answer. You would explain, draw these diagrams, plus you got to write all of it. You cannot cut short a diagram. The diagram, whatever is there, has to be drawn. You can cut short theory. Cut short the theory, otherwise, as I said, you'll write a never-ending answer. Okay? I hope you understood the whole thing. Wish you all the best. Do well.